Information and Communication Technology presents Educational Satellite Television Programs.
Hello, teacher. Hello, students. Welcome to today's lesson on nuclear energy. Several lessons ago, you were introduced to the phrase binding energy, and you performed an exercise using the isotope stability graph in your textbook. Today, we will look more closely at binding energy and the role it plays in the larger field of nuclear energy. Are you ready, students? Let us begin the lesson. You probably recall that binding energy is the energy required to disassemble a nucleus into the same number of free, unbound neutrons and protons of which it is composed. The nucleons must be far enough from each other that the strong nuclear force can no longer cause them to interact. In other words, binding energy is the energy required to hold the nucleus together or to split the nucleus apart. Along with the ratio of protons to neutrons in the nucleus, binding energy is one of the properties that determines nuclear stability. The greater the binding energy per nucleon of an atom, the greater its stability. If you were to add up the total mass of the protons and neutrons that compose an atom, you would notice that this sum is less than the actual mass of the atom. This missing mass, called the mass deficit, is a measure of the atom's binding energy. We will study mass deficit in more detail in our next lesson. For now, it is important to note that the net binding energy of a nucleon is found by calculating the difference in mass between the nucleus and the sum of the masses of the nucleons that make up the nucleus. In helium, the protons and neutrons are at almost exactly the same ratio. As nuclei become heavier than helium, their net binding energy per nucleon grows stronger and stronger until it reaches a maximum point. Students, please look at this graph, which shows the binding energy curve. Which element shown here do you think is the most stable? Why is it the most stable? Please write down your answers.
Students, let's get ready. Begin. Time's up. Let's get back to our lesson.
Welcome back, students. If you answered iron or Fe, you are correct. Iron is at the peak of our binding energy curve. As nucleons are added, the total nuclear binding energy always increases. However, so does the total disruptive energy of electric forces. This means that as protons are added, the force produced by protons repelling other protons increases. The main isotope of iron has 26 protons and 30 neutrons. This makes iron the most efficiently bound nucleus. Once you pass iron on the binding energy curve, the total disruptive energy outweighs the nuclear binding energy, and the elements become more and more unstable. Students, let us look at an example using deuterium. Deuterium, also called heavy hydrogen, is a stable isotope of hydrogen. Deuterium is most often represented as 2H because it has an atomic mass of 2. The nucleus of common hydrogen contains no neutron, but the nucleus of deuterium contains 1 proton and 1 neutron. Because the ratio of protons to neutrons is 1 to 1, there is a strong nuclear force holding this particle together. Deuterium can occur naturally in the oceans. In nuclear reactors, it is used in the form of 2H, 2O, or heavy water to moderate nuclear reactions by slowing neutrons. Tritium, or 3H, is another isotope of hydrogen. It is highly radioactive, or unstable, because it contains 1 proton and 2 neutrons. Students, what do you think might happen if you were to combine or fuse deuterium with tritium? In answering this question, think about the nuclear binding energy of each atom. A hint that might assist you is that one of the products is helium, which has 2 neutrons and 3 protons. Please write down your answers.
Students, let's get ready. Begin. Time's up. Let's get back to our lesson.
Welcome back, students. I am sure you did not have too much trouble with this exercise. As you can see in this diagram, when deuterium, which has one proton and one neutron, combines with tritium, which has one proton and two neutrons, it forms helium, plus one neutron and energy. As you learned in the last lesson, sometimes particles are emitted in order to achieve stability. In this case, the extra neutron is expended, along with a gamma ray, and a significant amount of energy is released. Binding energy reaches a maximum level because of the trade-off in the effects of two opposing forces. The strong nuclear force, which binds protons and neutrons equally to each other, and the repelling electromagnetic force, which acts between protons to force nuclei apart. For nuclei larger than about 4 nucleons in diameter, the additional repelling force of additional protons more than offsets any binding energy resulting from additional strong force interactions. Nuclei containing more than 209 nucleons, about 6 nucleons in diameter, are all too large to be stable and are subject to spontaneous decay to smaller nuclei. In future lessons, we will look more closely at what happens when we combine lighter elements and split heavier elements. Both of these reactions produce tightly bound elements and also give off energy. That is all the time we have for today's lesson. Until next time, thank you, teacher. Thank you, students.